So what is a OpenMP? OpenMP, stands for Open Multi-Processing. It is an API for the shared memory parallel programming. So it uses the compiler directives, runtime library routines, and environment variables. OpenMP supports the C, C++, and Fortran. It is based on the fork join execution model. This program fork join execution model in OpenMP is that is, the program starts with a single master thread. The parallel region creates a team of threads, and threads execute in parallel. At the end of the parallel region, threads join back together. So what are the parallel loops? Loops with independent iterations, and these enhance each iteration in this can be executed by the different threads. So most common form of parallelism in OpenMP is open, that is a parallel loops. And if you take the syntax of the parallel loop, and it is a pragma OMP parallel for, and these iterations are divided among threads. So loop variable is a private by default. All the threads share the global variables. And in this case here, the for loop, we are going to print this iteration percentage ID that is executed by the thread, and iteration and which thread is going to execute in this parallel for loops. So iterations may execute in any order, but output order is non-deterministic here. And what are the benefits of parallel loops? And parallel loops mainly reduce execution time and efficient CPU core utilization. It's very simple to implement, and also if you want to make any changes, and that is very minimal. And next one is, what is loop scheduling? The loop scheduling defines how loop iterations are assigned to threads. This is mainly important for load balancing, performance optimization. It is mainly controlled using the schedule type and the chunk size. And let us see the type of OpenMP schedulings, each one. So static, dynamic, guided, and auto these are the different types of OpenMP schedulings. So static is of where the fixed chunk assigned at a compile time. Dynamic means the threads take the chunks at runtime, whereas a guided scheduling type, here the decreasing chunk size over the time. And auto is a compiler, that is compiler automatically decides. And if you look at a static scheduling, where the equal chunks assigned in advance, this is a low overhead. This is best suitable when the workloads per iterations is uniform. And for example, there are 8 iterations. So suppose there are 4 threads. So each thread would get 2 iterations. And second, dynamic scheduling. Here the threads request the new chunks after finishing, and this is a higher overload and best for the uneven workloads. And this is mainly used when the iteration time varies. And what is the need for synchronization? The multiple threads access the shared data, so that can lead to the race conditions, incorrect results. So synchronization ensures the data consistency. And what is the OpenMP data environment? The OpenMP data environment defines how variables are shared or are private among threads in parallel regions. In OpenMP, when a parallel region starts, each variable gets a data attribute. This attribute determines visibility and lifetime of the variable across threads. So common data attributes in the OpenMP includes the shared. It is a single copy shared by all the threads. So changes by the one thread are visible to others. So the default for the global variables. The second attribute is private. So here each thread gets its own copy. So value is undefined initially here. And next one is a first private, like private but initialized with the original value. Next, the last private. This is a value, that is a value from the last iteration is copied back. Like suppose here you can see the pragma OMP parallel for last private of x, and in this for loop I equal to 0, I is less than 4, I plus plus x equal to I. So the last iteration value will be copied into this x, and that will be printed here. Reduction is each thread has a private copy that combined at the end, so it avoids the race conditions. This is best for the sum products, minimum, maximum. Next, default one is it controls the implicit data sharing behavior and forces explicit declaration. This is best for the large programs. This is a simple example to understand this data environment, like Pragma, OMP parallel private, and also the shared. And this is to get the number of threads, and then Pragma OMP critical, and then each thread would execute this P by A. So why data environment is important? So data environment prevents the race conditions, improves the program correctness. So it controls the memory usage, and this is mainly critical for the performance optimization. So data the OpenMP data environment contains attributes of variables and objects. So many constructs such as parallel, SIMD tasks, and accept the classes to control the data sharing attributes of referenced variables in the construct. The data sharing applies to whether the attribute of the variable is shared and is private storage or has a special operational characteristics, as I explained in the first private, last private, linear or reduction class. Yeah, welcome back. In this program, this shows how the different schedule types affect the loop execution here. This is again a very simple program, all static, dynamic, and guided scheduling concepts already included in a one single program. Like if you just could recall the static, it is a fixed iteration chunk size, it is very low overhead. Whereas the dynamic threads grab work at a runtime. This is good for imbalance. And the third one is a guided, it is decreasing the chunk size over time. So let us see the coding part here, OMP, and this is the way we can write this program into this drive. And before, let us connect to this runtime environment. Now let us see here, and this is how we can make use of this OpenMP API functions. In this case, like pragma OMP parallel number of threads. This is the way we can set the number of threads, and this is for scheduling static type, and chunk size is 2, and for I equal to 0, I is less than 15, I plus plus static, and this iteration number would be printed here and then executed by the thread number by this. The next one is a pragma OMP for loop, and this is for the dynamic. Again, the chunk size is 2. Like each time the compiler assigns the 2 threads. So next here it is going to print the iteration number and executed by the thread, that is a thread number, that is in dynamic scheduling. Next one is guided, and here also the chunk size same, and for I equal to 0, I is less than 16, I plus plus, like guided iteration number, and this would be printed here. So that is just to understand how the iterations are divided among the threads. Okay, so let us first run this. we yeah, now you can see writing OMP underscore shared.c is done. Next we can compile by using this GCC OpenMP. So now this executable file OMP underscore shed is available now. Now we can run this. So if we run this code, so this is output here. So iteration number 6 executed by the thread. In this case, you can see the static case. So static, how many? Like total 16 iterations. So it is 16 iterations. How static divided? Like here you can see here how many times a particular thread number is appeared. In this case, like up to this one. Here the static case, and this is how the iterations are divided among the threads. Like here in this case you can see here the thread 3 got a 3 instructions, and thread number 0 that got 4 instructions. Thread number 1 also got 4 instructions. Thread 5 got the remaining instructions. So that is in the static case. Like suppose if you rerun this code it again, then let us see here. Now the thread 1 also got the same number of instructions. Now this time thread 3 got more instructions than the rest, and thread 2 also got only 4 instructions now. And again if you execute it again, this time also it will change it. So next go to the dynamic case. Or let me copy. And guide it. Now you can see here in the guided case the different here the execution number of instructions executed by the threads are different. Here you can see there's here 4 and 4 almost 8 instructions being executed by thread 3 only. The rest of the instructions are executed by one only, 1 2 2 3 and 3. So this is how the static, guided, and dynamic scheduling, that is how the iterations would be distributed among the threads. Like suppose if you increase the thread size, let us just change this chunk size to, before let us just understand there are 4 threads, right? So now let us change this chunk size to 4, like at a time 4 instructions. At each time the 4 iterations would be assigned to a thread, and that I just changed to the in this static case. So let me run this again. So compile it and then run this. So now you can see here the static case 4 almost, because of like there are 0 1 2 3. So 3 got, and let me run this code it again. Now you can see thread number 0 got more number of iterations than the remaining. And now the thread number, yeah, the same. So like this. So this is how the different scheduling, open loop scheduling works: static, dynamic, and guided. This is based on the chunk size. And next one is the OpenMP synchronization constructs like first private, last private, private, public. Like when this, and these are the synchronization constructs. Those are I have already explained in the previous case. So let us move on to this open loop constructs. Yeah, and uh, this code is mainly to explain this variables, shared variables in the data environment. Mainly data environment are the OpenMP data environment attributes. So this example to explain mainly the shared variable, shared, how it works. And this is the way we can define like OpenMP parallel shared. And this x equal to x plus 1, this is a race condition here, final value of x. Let us run this and check. Because of, yeah, so here the final value, and like suppose if it is private, you can see this is the way we can use this private pragma OMP parallel private, and this is to get the number of threads, and then it is going to print the thread number and the value of x. And then this is the way we can compile using the GCC OpenMP. You can see here some this thread 1 x is updated by now the thread 0 and thread 1, like randomly we are printing this thread because the default number of threads in this runtime environment uh, is 2. Next one is a first private, and this is the way we can, so here this, here also just we initialized a variable x that is to 5, and then the parallel region and the first private, and here we are going to print this thread number and X. And next one is the last private, that is to copy the last iteration value. This is so this is the last iteration value 4. Like for example, here if I mention some 10, this is last iteration value that is always copied by using this last private. Next, reduction, that is mainly used for this aggregate functions. That's it, there's nothing. So this data race already explained in the previous case. So how to fix this data race, that I have already explained. So here how we fix this data race using the critical or any other synchronization construct, because critical means it allows only one process or one thread at a time to update. So now this counter would be updated in the parallel region. So this is in the critical. So once a thread enters here, it is once this program, once we enter into this parallel OpenMP parallel, then the task would be created in the parallel, and then but because of this presence of this critical region, only one thread is allowed to enter into this critical region and update the counter value. That's why we'll get exact. So there is no, so we can, this is the way we can solve this race condition. So that's it.